Welcome to the deep dive. We know you want to get straight to what's new and important. So today, we're diving into back contact solar cells. Hearing a lot about these lately, they seem like a pretty transformative step in solar tech.
They really are. The core idea is simple, actually. You know how normal panels have those grid lines on the front?
The electrodes, yeah.
Right. Well, back contact, or BC tech, just moves all of that hardware to the back of the solar cell.
Which makes immediate sense. Get that stuff out of the way, let more sun hit the silicon.
Exactly. More light absorption. Now, people might hear a few different names thrown around. There's LONGi's HPBC, Aiko Solar has ABC.
Right, and SPIC's IBC, PBC, JINKO BC too. Lots of acronyms.
Yeah, haha. So our mission here is to unpack why putting contacts on the back is such a leap forward, and what that actually means in practice.
Okay, let's get into it. Manufacturing these sounds.
Yeah.
Complex, all the connections hidden away. I saw something about infrared non-contact welding. Sounds high-tech.
It is pretty neat. So instead of a hot soldering iron touching the cell, they use focused infrared light to melt the solder paste.
Ah, so no physical pressure.
Precisely. That's the key. It minimizes physical stress on the silicon wafer itself. Less stress means fewer microcracks, which can hurt performance and longevity. Plus, the heat is really uniform.
And that helps maintain one of the big benefits of BC cells, right? That low temperature coefficient I keep reading about, like how well they handle heat.
Absolutely. BC cells generally have a great temperature coefficient, around minus 0.26% per degree Celsius. So when the panel gets hot, which they do, they lose less power compared to, say, older PRC tech or even TOPCon sometimes.
Okay, so that welding technique helps preserve that advantage.
It does, and it's especially good for cell types like HPBC and ABC that might use delicate heterojunction layers. This gentle welding keeps the power loss after connection really low, like less than 0.5%.
Wow. Okay, but you can't do this intricate stuff by hand on a production line. The automation must be intense.
Oh, completely. Automation is critical. You've got automatic feeding with robotic arms, placing the cells with insane precision. We're talking sub-millimeter.
Okay.
Then things like isolation paper removal. Sounds minor, but they use vision-guided systems to peel off protective layers without leaving any residue or causing contamination. Very careful work.
Right. Every little bit counts.
Yeah.
What about actually making the electrical connections stick?
That's where automated dispensing comes in. It precisely dabs on these conductive adhesives, often silver epoxy mixes, onto the contact points on the back.
For good adhesion and conductivity.
Yep. And then you've got high-speed welding to attach the bus bars, those strips that collect the current. These machines can churn through like 3,000 cells an hour. It's necessary for scale and works for various BC layouts like TBC and IBC.
Okay, so they can make fast and precision.
Yeah.
But how do we know they're reliable? Any checks along the way?
Crucial question. They use inline EL testing, that's electroluminescence. Basically, they make the cell light up and take a picture to see internal defects, like cracks or bad connections.
Like an X-ray for solar cells.
Sort of, yeah. And the accuracy is super high, over 99%. So any dodgy cell gets flagged right there on the line. That real-time quality control is huge for the final module's reliability.
Okay, sophisticated manufacturing, checks in place. Let's switch gears to the payoff. Why would someone choose BC tech? You mentioned efficiency earlier.
Yeah, superior efficiency is the headline, really. Mass production efficiency is hitting like 26 to 27% now. Compare that to maybe 24, 25% for good TOPCon.
That's a solid jump.
It is. And theoretically, because there's zero shading on the front and light capture is over 95%, the limit is way up there, near 29%. So there's still room to grow.
We touched on the low temperature coefficient. Better performance in the heat. What else?
Well, aesthetics and architectural integration. This is a big one for some markets because the front is just clean, uniform black or dark blue, no visible line.
Looks much sleeker.
Totally. Makes them really attractive for putting on buildings, not just on racks. Think BIPV building integrated photovoltaics. LONGi's HPBC is doing well in high-end homes for exactly this reason.
Makes sense. How about durability? Real-world stuff like shade.
They generally have enhanced reliability. Putting the connections on the back inherently reduces the risk of hot spots forming if a small part of the cell gets damaged or dirty.
Okay.
Plus, many designs use things like distributed bypass diodes and have low internal resistance. This helps the panel maintain output, maybe over 90%, even if one part gets shaded, which happens all the time in reality.
Right, a branch falls, morning shade. Okay, the elephant in the room. Cost. All this fancy tech sounds expensive.
Well, yes, currently the upfront cost is higher than mainstream tech like TOPCon. That's true, but
yeah.
there's a clear path towards cost efficiency. People are working hard on it. Things like using silver aluminum paste instead of pure silver, developing better laser processes. The projections suggest they could reach cost parity with TOPCon maybe by 2027 or so.
So the premium might shrink significantly. Interesting. And looking further out, where does BC fit in the tech roadmap?
That's also exciting. The market outlook and technological synergies look good. The basic BC platform seems quite compatible with other advanced cell concepts, like layering it with TOPCon structures or HJT or even the next-gen perovskites.
Ah, so it could be a foundation for future hybrid cells.
Potentially, yeah. It offers a great base design to build upon.
Okay, so summing this up, back contact isn't just a small tweak. It's a pretty fundamental redesign moving contacts to the back, enabled by some very clever, precise manufacturing.
Right, like that infrared welding and the inline testing.
And it delivers real benefits. Better efficiency, works better when hot, looks cleaner, and seems more reliable, especially with shading.
That's the gist of it. Better design, better manufacturing leads to better real-world performance and potentially longer life.
All right, lots to digest there. So here's a final thought for everyone listening. Given these clear advantages and this potential path to lower costs and integration with future tech,